Hello, and welcome to your All the Stuff You Need to Know math lecture. So before we start, I just want to say everything's fine. You're going to be fine. I know math can be really anxiety producing or stressful for some of you. We're just going to review some key math ideas that you're going to need to do well in this class. And I'll let you know which ones you'll actually need to know how to do and calculate, and which ones are just ideas that you're going to need to use later on in the class. The first topic I want to review are logarithms, and logarithms are just the opposite of exponents. So what I mean by that is when you have log base b of n equals x, that's just kind of a fancy way of writing b to the x power equals n. And you can see where we have the same variables in both of these equations. So we have n, we have x, we have b. So logarithms basically answer the question of what power do I have to take b to in order to get n? And one of the useful things about logarithms is that it takes positive numbers in, so those n's can be any positive number, and it actually transforms them to take up the entire number line, negative to positive. So you can see on this graph of log base 2 that any number between 0 and 1 will give us a negative number. And that's true no matter what the base of your logarithm is. If you plug in log of some number between 0 and 1, you're going to get a negative value. Anytime you plug in a number greater than 1, you're going to get a positive value for that log. And that's because we've just defined for logarithms that any number to the power of 0 is equal to 1. One thing that we love about logarithms is that they help with multiplication. Now, multiplication is just doing addition a bunch of times in a row, but it can be a little bit computationally expensive or difficult to do. With logarithms, because of the way that we work, if we take the log of two numbers multiplied together, let's say x times y, that's actually equal to the log of x plus the log of y. So we've turned on the left-hand side a multiplication problem, which might be kind of difficult, into a very simple addition problem. Which brings me to a very silly and a very popular joke about logarithms. So Noah is getting off his ark and he's checking on all of his animals, seeing if they're able to reproduce and are living well. And he checks on all of the animals and all of them are doing well, with the exception of a pair of snakes. So Noah goes up to them and says, "Hey, what's going on? Why aren't you reproducing? Is there something wrong?" And the snakes say, "Oh, well, could you just chop down some trees for us and let us live in what remains of them?" And Noah goes, "Okay," and does so. Then a couple of weeks later, Noah comes back and everything's great. The snakes are reproducing and they look great. So we ask them, "Oh, why did having all of those chopped down trees help you reproduce?" And the snakes say, "Well, we're adders. We need logs to multiply." So one last thing I want you to know about logarithms. So remember when I said that logarithms are just the opposite of exponents. So if we want to undo a logarithm, we just take the base to the power of that logarithm. So for instance, there's a logarithm called the natural logarithm, which its base is e. So we say if there's a natural log of x, if we want to undo this logarithm, we're just going to say the base e to the power of the logarithm, ln of x, and that equals x. Similarly, if we have log base 10, then we can say 10, the base, to the power of log base 10 of x, that also equals x. So again, logarithms, exponents, opposite, so when you apply them together, you're undoing the logarithm. Next, let's talk about derivatives. Derivatives are an instantaneous rate of change. Basically, they answer the question, how is this function changing at a particular point in that function? So for instance, here, we could look at a derivative that tells us at this point right here, how is the function changing? Is it increasing? Is it decreasing? Or is it not doing anything at all? What's important to remember about derivatives is that when they're positive, it means a function is increasing. When they're negative, it means the function is decreasing. And when they're 0, it means that the function is flat at that point. And that's really useful to us because flat points in a function are often minima or maxima. And a lot of times in data science, we want to find the min or the max of some function. Next, let's talk about integrals. Integrals are the opposite of derivatives, and the way we're going to use them in data science is to find the area under different curves. So for instance, if we have this very weird shaped green probability distribution, we might be interested in finding out what is the probability that a value will land between these two boundaries. Well, the way that we calculate that of saying what is the likelihood that a variable will be in this dark green area is by using integration. So again, both with probabilities or general areas under a curve, we're going to need integration in order to do that. Next, I want to talk about the elbow method, which is oddly going to come up a lot in this class. So let's do a really silly example first. Say your friend can get a little annoyed with you, and you don't want them to be annoyed with you, and you want to decrease the amount of annoyance that they have for you. And one way of doing that is by buying them Starbucks. So we're going to replace this here, and we're going to say number of Starbucks. And here is going to be their annoyance with you. Now, you might be asking yourself, as the true data scientist that you are, how many Starbucks do I need to buy my friend before they're at an acceptable level of annoyance with me? Well, let's assume that every time you buy them Starbucks, it does decrease their annoyance for you a little bit. So you can see in this blue line on the graph, let's say that this is their level of annoyance, and if you buy them one Starbucks only in a month, they're going to be that level annoyed with you. If you buy them 2, they'll be here, 3 here, 4, etc. So you can basically see as you buy them more Starbucks, their level of annoyance with you decreases. But there's diminishing returns. The first Starbucks decreases their annoyance with you a lot and is very worth the steep price that Starbucks charges. Now, the second Starbucks, it does a lot, but not as much, and the third Starbucks even less than that, and fourth and fifth, and they're all decreasing annoyance, but not that much anymore, and at a certain point we have what's called diminishing returns. Yeah, it makes your friend a little less annoyed with you, but by less and less each time you buy them Starbucks. This graph could basically tell you when should you stop buying them Starbucks. And one way of deciding that is by using the elbow method. In this method, we basically look at the graph like it's an arm, and we try and find where the elbow is. In this case, it's pretty obvious. It's right here. This is the point at which there are diminishing returns. The point at which, yeah, you can buy them a Starbucks, it'll make them a little less annoyed, but it's not really worth it anymore. And this elbow method is really useful for selecting much more than the number of times that you buy your friend Starbucks. And it'll actually come up a lot in this class. So just remember, when we have a graph like this where we're trying to decrease something, we can use the elbow method to figure out where are we getting diminishing returns? Where is increasing the number of Starbucks orders not really doing much for us at all? Let's talk a little bit about matrices and vectors. Matrices and vectors are basically just different ways of thinking about data structures that can contain data for us. For instance, matrices, for example, are a way that we can think of just like data sets that we would have. For instance, imagine an Excel spreadsheet. That's basically what a matrix is. It has rows and it has columns, each of which represent different things. For instance, a row might be like a person and a column might be their height. There are also special matrices, like a correlation matrix, that come up a lot in data science, and a matrix is just a convenient way to store those values. While a matrix has rows and columns, a vector has only rows or columns. So for instance, here we have a column vector because it's just a single column. It doesn't have 2 dimensions like a matrix. One thing we might want to do with matrices and vectors is multiply them. So here we have a 2 by 2 matrix. It has 2 rows and 2 columns, and then a 2 by 1 vector because it has 2 rows but only 1 column. Now we know that we can multiply them together because their inner values, see this on the right and this on the left, match. That means these are compatible to be multiplied together. Now in order to do so, what we're going to do is we're going to take the column from this vector and the row from this matrix, and we are going to multiply each element together. So we're going to take 1 times 1 plus 2 times 3, and that's going to be 1 plus 6 equals 7. Next, we're going to take that same column from the vector, but using this row from the matrix, and then we are going to get 1 times 0 plus 3 times 1, and that's going to give you 3. So the result of this multiplication is going to be a vector of 7 and 3. Now, I promise you're not going to have to do a lot of these by hand and rarely without a formula or a friend to help you, but I just want you to understand that that's how matrix multiplication works. The next thing I want to review with you is eigendecomposition, which is just a fancy way of saying calculate the eigenvectors and the eigenvalues for a matrix. We can think of a matrix as just a way to transform different points via matrix multiplication, like the one we just did. To give you a brief overview of why this is so important, eigendecomposition and calculating those eigenvalues and eigenvectors basically gives us information about a matrix. So sometimes we want to know more about the matrix that we're looking at, and we can use the eigenvectors and the eigenvalues to get that information. On a more technical note, you can think of that matrix as a transformation that's just stretching or squishing vectors when you do that matrix multiplication. So for instance, let's start off with this square here. You can see that this square has corners at 0, 0, 1, 1, 1, 0, and 0, 1. Well, what happens when we take those vectors and we multiply them by the matrix on the left? We'll get some sort of new shape. So let's start with the bottom left corner, 0, 0. We are going to multiply this vector by this matrix, and I'll do this one by hand because it's very easy. So we're going to get 0 times 1 plus 0 times 5 equals 0. And then 0 times 0.5 plus 0 times 1 equals, make sure that's a multiplication, 0. So our new point is actually our old point, the vector 0, 0. So I'm going to add that to our new graph here. All right, now that we've done one by hand, let's let a computer do the rest of them for us. So the point 1, 1 at the top right corner now becomes 1.5, 1.5, so we'll draw that in here. The point 1, 0 becomes 1, 0.5, so we'll draw that in here. And the top left corner, 0, 1, becomes 0.5, 1, so we'll say 0.5 and up 1. So now we've created this entirely new shape, and that's because the matrix transformed our space. So I'm going to go ahead and color that in here. So you can see basically the matrix stretched and squished our original square, and we might want to know a little bit about that stretching and squishing. For instance, what directions are the main directions of stretching and squishing? We can do this by looking at whether or not there are vectors that aren't actually moved or rotated, they're just stretched or squished. Those are going to be the main directions of stretching or squishing. For instance, we originally had this diagonal vector in our square, and in our new shape, it didn't actually move to the left, to the right, or rotate at all. It just got a little bit longer. It went from 1, 1 to 1.5, 1.5. So for instance, that's a main direction of stretching, and that tells us a little bit about what this matrix is doing. So basically, we want to find a vector where when we multiply it by a matrix, it's the same thing as just multiplying it by a single number, so either making it bigger or smaller. To do that, the formula is A, so the matrix times a vector equals lambda times a vector. So when we multiply a matrix by a vector, it's the same thing as multiplying that vector by a number. Now, I'm going to let a computer do all of this calculation for us, but it turns out that the eigenvectors of this matrix are 1, 1, which we already saw here, right? That's this vector. When we do the matrix transformation, it just gets longer. And the other one is negative 1, 1. In other words, negative 1 up 1, this vector. This one doesn't actually change or rotate at all. It just gets squished a little bit. These eigenvectors or directions have numbers associated with them called eigenvalues. And these basically just tell us how much things are stretched or squished. In this case, the eigenvalue for the 1, 1 vector is 1.5, which makes sense because we saw that it gets longer, it gets stretched when we apply the transformation. The eigenvalue for the other vector is 0.5, which again makes sense because that vector, even though it's not changing directions or twisting or anything, it is getting squished, so it makes sense that it's being multiplied by something smaller than 1. Now, I'm never really going to make you calculate eigenvectors or eigenvalues, but it's important you know what those things are theoretically. The eigenvector are those directions in which vectors don't change. They just get bigger or smaller. And the eigenvalues are the amount that we scale them. Eigenvalues bigger than 1 means something gets bigger. Eigenvalues less than 1 means something gets smaller. And again, this is important because eigenvalues and eigenvectors give you information about a matrix. And we have lots of matrices that we'll look at in data science, from data matrices to covariance or correlation matrices. And sometimes the eigenvalues and the eigenvectors are a good way to extract information from those matrices. Speaking of covariance, let's talk about it. So variance and covariance are very similar concepts. Variance is basically the idea of how spread out data is. So you can see on the top line, we have a bunch of data points, and on the bottom line, we have a bunch of data points. But the ones on the bottom are more spread out, so it has more variance. The formula for variance is here. It's basically the squared deviation of every data point from the mean. So how far is a data point from the mean? Square that and take the average. Covariance is very similar, and actually you might recognize how similar this formula is to the variance formula. Covariance, instead of just a single variable, is looking at two variables, and covariance is a measure of whether or not they move together or not, and how strongly they move together. For instance, when we look at these two graphs, we can see that this graph has better or higher covariance. These two variables move together a lot more strongly than the ones in the right-hand graph. So again, higher covariance means a stronger relationship. When one goes up, the other goes up. Next, let's talk a little bit about the normal distribution. Now, I'm sure you've come across this at some point, but the normal distribution is just a probability distribution that is really useful to us. First of all, it's really well behaved. It's symmetric, it's unimodal. You may have seen this as a bell curve in one of your high school classes. And the nice thing about a normal distribution is that we know a lot about it. Everything from the area under it to the formula for calculating it, we just know a lot about the normal distribution. So when we can assume that variables or parameters or other values are normally distributed, it just helps us calculate things when they're normal because, again, we know a lot about the normal distribution. All right, now let's talk about data types. So when we have data sets, we have different variables that have different types. For instance, height or weight or GPA are all examples of continuous data. Continuous data is data that has basically an infinite number of values it could theoretically take on. For instance, I might be 5 foot 2.14365 inches. And you might be 6 foot 3.27466 inches. So continuous variables are basically what we're used to seeing like numeric data, right? Something that could take on like a decimal or something like that. When data isn't continuous, another thing it often is categorical. These are data variables that are groups, basically. So for instance, I could ask, are you a freshman, a sophomore, a junior, or a senior? Those are groups, and there's not an infinite amount of options of values that you could have for that variable. You're one of 4 things, freshman to senior. Another example of a categorical variable might be your major. You only have a certain number of choices of majors here at Chapman, and you're one of them. There's not an infinite number of values that that variable could take on. But categorical variables come in a lot of different flavors. So let's start with the basic one, nominal. Nominal data is something that doesn't have a meaningful order. For instance, if I went around the classroom and said, what's your favorite color? Red, blue, green. I would be able to put you into groups, red, blue, or green, and there's no real order to them. I can't necessarily say that red is higher or better or green is worse than any of the other colors. Because there's no order, it's a nominal variable. It's a categorical variable, but there's no relationship or order between the 3 categories. One really simple version of nominal data is dummy variables, which only have 2 categories. For instance, registered to vote versus not, or goes to Chapman, doesn't. Now, while nominal variables don't have any relationship or order to the groups that they exist, ordinal data does. Ordinal data is a categorical variable where there is a meaningful order that we can use to organize the different categories. For instance, I can look at the type of degree that someone has. So we might have a high school diploma or GED, an AA, a bachelor's, a master's, or a doctoral degree. Now there's still categories, right? Everyone's in a specific category. You can't have infinite values or infinite ways that you can be in that category. But there is a meaningful order. We could, for instance, organize it from least to most education, from high school diploma to a doctoral degree. So because there is an order, it's not nominal anymore. It's an ordinal variable. So again, ordinal means there's an order and it's a categorical variable. However, ordinal variables don't have to have equal spacing between each of the categories. For instance, in the example I gave, when you go from high school degree to AA or AA to bachelor's or master's to PhD, it's not necessarily that the difference between those or the change between each successive category is equal. If it were, then we would have an interval data type. Interval data is when you have an order and the difference between each of your categories successively is the same. For instance, let's say I show you a picture of a really cute corgi, and I ask you to rate this corgi on a scale of 1 to 10, where you can only pick 1, 2, 3, 4, all the way up to 10. Now, I could technically put you into groups, right? Here's a group of dog haters who rated this corgi a 1, and a group of dog lovers who rated this corgi a 10. And there's also a meaningful order. We could rank you from hates this corgi to loves this corgi. But in addition to the order, we also could argue that the distance between rating the corgi a 1 and rating it a 2 is equal to the distance between rating it a 6 to rating it a 7. Because these values or these groups are equally spaced, this categorical data is interval. It has an order and there is equal spacing between each of the options. Now, when we have interval data, we basically treat it as numeric data or continuous data because usually it is. So for instance, if I asked you to rate this corgi on a scale of 1 to 10, we can basically treat that like a continuous variable. So to review, for categorical variables, the most basic level of categorical variable is nominal. There are groups that you can be a part of. There's no real order to them, like your favorite color being red, green, or blue. Next, we have ordinal variables. Ordinal variables are categorical variables that do have an order, like the amount of education that you have. Next, we have interval. Interval data is basically ordinal data where we also know that the distance between each of our categories is equal. And usually this is going to be some number, like again, the 1 to 10 corgi rating scale. Okay, enough categorical. Next, let's talk about Boolean data, which is actually kind of categorical as well. Boolean data is sort of like dummy data where it's either yes or no. You're registered to vote, you're not. You're married, you're not. Boolean data, though, specifically is just a true or a false value, whereas dummy variables are zeros and ones. Basically the same thing, but slightly different. Last but not least, we have text data. Now, text data may seem to you like categorical data, but there are some things that are text data which aren't really categorical. For instance, if you've ever taken a survey and they had a free response question that they said, what do you like about this app? And there's a text box for you to type in your answer. Or anytime you've had to enter your email address or your actual physical address. These things are text, similar to a categorical variable, but unlike a categorical variable, there's not groupings in the variable. For instance, when I asked your favorite color, there were distinct options. You could have chosen red, blue, or green. When you enter your address or your email address, it's still text data like the categorical variable, but there's no groups. Basically, my rule of thumb for text versus categorical data is, do I expect a lot of people in this data set to have the same value? When I ask if your favorite color is red, blue, or green, I do expect a lot of you to be red, green, or blue. But when I ask you for your email address, I don't expect people to have the same email addresses. Even with something like a physical address where 2 or more people in your data set might have the same address, it's not like I expect big groups of people to have the same value when entering their address. Next, let's talk about probability. Probabilities are basically a measure of how likely we think it is that something is going to happen. For instance, I might say there's a 90% probability that I'm going to get an A in this class. One way we can calculate probabilities is with continuous values. For instance, if we have a normal distribution, we might ask, what is the probability that a number will fall in this darker yellow section of the distribution? We can also have probabilities with discrete events, like whether or not it's raining and whether or not I brought an umbrella. For instance, here you can see that it is much more likely, as it is in Southern California, that it will not rain compared to the chance that it will rain. Maybe this is about a 75% chance of not raining and a 25% chance of it raining. In general, the formula for a probability is the number of times that something happens divided by the total number of things. So for instance, let's say I want to know, what is the probability that Chelsea is going to get coffee? Well, if out of a week I get coffee once, the probability would be 1/7, whatever that decimal is, because the number of times I got coffee, 1, is divided by the total number of days. All right, let's talk about conditional probabilities. Conditional probabilities are just like regular probabilities, but with extra steps, which I'll show you. So let's look at a plain probability first. I'm going to use this P notation, which means the probability of. So we're going to look at what is the probability that I bring an umbrella to campus. So in this picture, you can see that's represented by this kind of transparent area. So this is a little high, but let's say it's about 20%. 20% of the time, I will bring an umbrella to campus. Well, let's look now at a conditional probability. We can say, what is the probability that I bring an umbrella given, that's what this little pipe operator means, that it's raining? So now, when we calculate this conditional probability, we're not just looking at overall how often do I bring an umbrella, which we estimated to be about 20%. Instead, we are looking at just the times when it's raining. So we are going to go ahead and basically ignore everything on this half of the circle. When we have a conditional probability, what we're doing is saying, let's only look at cases that we know it's raining. So everything after that given, we're saying, assuming we know it's raining, let's look at the probability that you bring an umbrella. Well, now that we're ignoring basically this entire right half of the circle, the probability of me bringing an umbrella is pretty big compared to me not bringing an umbrella. So the probability of bringing an umbrella just generally is pretty low. The probability of me bringing an umbrella given that it's raining is pretty high. All right, let's think of an example that's a little closer to home. Let's assume that the probability of being a business student is 0.1, about 10%. Now let's look at the conditional probability of P business student given you're taking 392. Well, that's a lot higher. In my classes, it tends to be about 50%. So given we're only looking at people in the class CPSC 392, the probability of being a business student is about 50%. However, just in the general population, the probability of being a business student at Chapman is probably about 10%. I'm actually making these numbers up. So you can see the difference between a regular probability and a conditional probability. The conditional probability has a condition. It basically restricts the denominator of our probability. In the probability of being a business student, the denominator is every student at Chapman. In the conditional probability, our denominator is restricted to people who are taking CPSC 392. All right, let's talk about something related to probability, which is odds. Now, if you're really into sports betting or betting on horses or something, you're probably familiar with odds. Odds are just a different way of representing probability, and the formula for odds is probability over 1 minus probability. In other words, the odds basically tell you how many times more likely it is that something will happen versus it not happening. So for instance, let's say that I have a probability of 50% that I'm going to get coffee before my next class. Odds that I get coffee are the probability I get coffee times 1 minus the probability I get coffee. Well, that's just 0.5 divided by 0.5. So the odds, 1, represent the fact that it is just as likely that I will get coffee as that I won't get coffee. Now let's look at the odds that I will fill my water bottle before class. Let's say the probability of me filling my water bottle is 0.9. So the odds would be 0.9 divided by 0.1, which equals 9. It is 9 times more likely that I am going to fill my water bottle before class than that I won't. Odds that are greater than 1 mean that it's more likely that something will happen than it won't. Odds less than 1 mean that it's more likely that something won't happen. For instance, let's say that we're playing in a soccer game and the probability that I score a goal is 0.4 or 40%. The odds that I score a goal are going to be 0.4 over 1 minus 0.4 or 0.6, and those odds are going to equal 2/3. In other words, it is 2/3 as likely that I will score a goal as not, meaning it's more likely that I'm not going to score a goal. Last but not least, let's talk a little bit about the difference between inference and prediction. So when we have a model that estimates something, like say I have a model that estimates your cat's weight based on its height and age. When we have that model, there might be 2 things that we care about. One might be the output of the model. Whatever height that the model is spitting out, we want it to be accurate. So you can imagine we're putting into our model the height and the age, and we're spitting out the weight. Now, one thing we could focus on is just, hey, is this number that's coming out, is this accurate? When I give it new cat information, is it accurately predicting their weight? That would be a focus on the prediction of the model. We don't really care what's going on in here as long as what's coming out of that model is accurate. On the other hand, we could do inference. Inference basically cares about what's going on in this model. So we want to make sure that the way that the model represents the relationships between height and weight or age and weight for your cat are accurate to the real world. We're basically trying to learn something about the structure of the world from our model, so we need to make sure that that model is accurately structured. And that's the difference between inference and prediction. They can sometimes go hand in hand, but prediction inherently cares more about the output, and inference cares more about the structure of the model. In data science and machine learning, we unfortunately often focus a lot on prediction, and sometimes that makes sense, right? If something can predict whether or not someone is going to default on a loan, maybe we don't really care why. We don't care about the structure of the model as long as the answer we're getting is accurate. But other times we might care about that structure. We might want to make sure that the information we're putting into the model is getting used by the model in a way that's accurate. So just wanted to put this into your heads that there is a difference between inference, caring about the structure of the model being accurate, versus prediction, just making sure that whatever comes out of the model is good. In this class, a lot of the things we're going to be doing is going to be focusing on prediction. We're going to be assessing the output of our model to make sure that it is accurate. All right, thanks for sitting through this one. That's all I have for you. I will see you next time.